So basically in this proof what we have to do is we have to prove that every Hilbert space is reflexive. So we start with H, let H be a Hilbert space, and let xt be the Riesz representation of T, which is an element in the dual space of H star. Now from Riesz representation we know that T of x can be written in this way, and the mapping psi given by psi from H star to H is antilinear, it's bijective, and it's isometric. And observe that H star is a Hilbert space with respect to the inner product. So the first question that rises up is why the dual space of a Hilbert space is a Hilbert space. So we know that in the dual space of the Hilbert space H, so let x belongs to H, and let me write it here, let x belongs to H and T belongs to H star. So what happens is the inner product defined in the dual space, in this space, between any two elements. So let me write two elements, T1 and T2 belonging to H star, and I write the inner product T1, T2, and I define it as now psi of T2. So if you remember about psi T, this mapping is antilinear. So antilinearity just means that in the inner product, so what I mean by antilinear is that suppose psi is my antilinear operator, and well, essentially it says that psi of T1 plus T2 equals to psi T1 plus psi T2. The other thing that it says is that psi of, say, CT is equals to C complex conjugate psi T. So that's the property of antilinearity, and it's bijective, means the usual term, and isometric. I have this mapping psi, which is antilinear, bijective, and isometric, and I observe that H star is a Hilbert space because the norm, the soup norm, so the norm on any space is given like this. So I know as of now that H star is a Banach space because a dual space of any space is a Banach space, and the norm, the usual soup norm on this Banach space is given like this. Now I need to prove that this is equal to the norm generated by the inner product, and this is how I do it. So let me write it down for you. Let me write it down. So I see that my inner product, so I write it as inner product of T1 and T2 defined as is a mapping from H star to H. So now since this mapping takes me to an element in H, now I know that H is a Hilbert space. So the elements here, they belong to my Hilbert space H. So I can take an inner product, and I see that, so this is how I define inner product on H star. So H star, so let me write it down. So the inner product in H star is defined like this. And now this is the inner product in H star. And now I need to show that the norm generated by this inner product, so we have seen in the very earlier videos that, you know, this inner product generates a norm and the metric is induced by the norm and things like that. So when this inner product gives you a norm, a notion of a norm, and when this norm, let me write it down as is, I write 3 here because I want to separate it from norm in, say, a different norm, like the norm that I defined above. I wrote that the norm of t is equals to the sup of tx, norm of x is equals to 1. Now I want to differentiate it from this norm and this norm. Finally I want to prove that these two norms are equivalent, and the way I do it is I start by writing just a definition. So the norm induced by this inner product, so let me just write it down. Let me just copy this definition down here. So if I want to generate a norm with the help of this inner product, I write it as, okay, but now I know that this t can be replaced by psi t, because that's what's the definition. If you just look at this definition, it would have, you should have no problem in understanding why this t is replaced with psi t. So in fact I think I have done the same calculation here. Yeah, that's it. So this t is replaced with psi t because of this definition. Yeah, now it makes more sense. And the psi t, now first of all, one thing we have to note down is that it is norm of t square, because only then I can write it like this. T is replaced with psi t, and then psi t square, or the norm of psi t square. So since psi is an isometry, I said it's an isometry, so in isometries what I have is psi t is equals to psi t. That's the usual case in isometries, so that's equal to the norm of t square, and this norm of t was my usual norm. So I see that the norm generated by the inner product is equal to this norm here, and thus I can say that the dual space of my Hilbert space is also an Hilbert space. Now the next thing that I would like to talk about is, now when I take a f belonging to h star star, I know that according to the Riesz representation theorem, there exists a tf belonging to h star with this. So in the case of Riesz representation, it was always between h and h star. I used to say that operator t applied to an element would give me something like this. So there exists an isometric isomorphism between, how to say it, something like this, which is, now the psi is antilinear, bijective, and isometric. And now, yeah, if I adapt to the same case from h star star to h, so I have f in h star star and to h star, that should be right. So from, if I have some f in h star star and apply it to something in h star, so it's saying that according to the Riesz representation theorem, there exists a tf belonging to h star with this property. So I just use it, I just make use of the Riesz representation theorem again to write f of t in this way here for my Hilbert space. Now what I do is, by writing it in this way, I can make use of this definition here and then just replace it with psi tf and psi t, where for all t belonging to h star. And the next thing that I would do is that I give a value xf to one of the psi tf. So if you remember, psi was taking me from h star to h, so it's completely valid to set me some xf belonging to h as the value of psi tf. and thus I can replace this definition here. I can take it this and replace it by xf, and now I invoke the Riesz representation theorem again, and I write it in this way. I can write xtf as this, and I know that this I was linear isometry, so according to the rule of linear isometry, t of x is equals to I of x of t, and hence I find out that for each f belonging in H star star, there therefore exists a unique element or an xf belonging to H with I of x is equals to f, that is I is surjective. So that's what I wanted in order to show that my Hilbert space is reflexive, or any space is reflexive. I have this linear isometry. If I prove that this linear isometry is surjective, then I can show that my space is reflexive, and that's exactly what I'm doing here. So the norm space X is uniformly convex if all sequences xn and yn on its unit circle have the property that the norm of xn plus yn by 2 tends to 1 as xn minus yn tends to 0. So when these points come close and close to each other, then the norm would of course tend to 1, as you can see from the definition. Now we say that the space R square equipped with the L2 norm is uniformly convex, and this is the normal usual square norm that I take in R2, and the points xn and yn come together as the midpoint of the line segment xn yn approaches the unit circle. So it's just saying that these points starts coming together, and as these points starts coming in this direction and this direction, this line will obviously get smaller and the midpoint will move closer to the circle. So next thing that we do is all Hilbert spaces are uniformly convex. So in order to prove that, I take a Hilbert space H, and then I take two sequences xn and yn on its unit circle. Now it follows from the parallelogram identity that this equation holds true, of course. Now I see that as xn and yn tends to 1, this whole thing tends to 4, and this thing would tend to 2, so this whole thing would tend to 0, which would imply that this thing here would tend to 0, and that's exactly what I want from a uniformly convex space. And the next thing that I want to show is that the uniform convexity of Banach spaces. So in order to do that, I have to look at this trivial result, and I make use of this result to prove that all Banach spaces are uniformly convex. This lemma that, so let's start, like p is greater than 1 by p plus 1 by q equals to 1. Now first thing I have to prove that this psi, which goes from Lp omega to Lq omega star, is an isometry. By isometry I just mean that psi of f, norm of psi of f, where's the formula, let me check. So this is essentially what I mean by isometry. Psi of f, norm of psi of f equals to norm of f. Now how do we do that? How do we prove that it's an isometry? So the very first thing that I do is that I prove that the psi f is an element of Lq omega star. Why? Because this g is an element of Lq omega. So when I show that, if I want to define it like this, I have to show that that psi f is an element of Lq omega star, and the way I do it is, okay, I write the definition, and with Holder's inequality I can split it into two parts and write it like this, but I just replace this integral of fg with the definition of integral of fg, which is just nothing but psi f of g, and then this is also less than equals to norm of p norm of f and the q norm of g, so I can say that this thing is bounded, well, psi f is obviously linear, and now I say that psi f is linear, so means that psi f of g1 plus g2 is equals to psi f g1 plus psi f g2. So first thing is linearity, and second I show that the psi f is bounded as an operator, so I say that psi f belong to my space LQ omega star, because my assumption was that G is an element of LQ omega. Now I know that I need to show the next thing, that this psi is an isometry, and the way I do it is, again, I define this f tilde as this function here, and I show that the norm of f tilde, the q norm, or the qth power of f tilde is to the pth power of f. And how would I show this? So the relationship between here to here is pretty much simple. You just substitute the values, and the next thing I do is I take integrals on both the sides. So if I take integral on both the sides and raise it to the power 1 by q on both the sides, I basically get this equation here, these two parts here, and from there, from these two parts, I just integrated on both the sides and I raised them both to the power 1 by q. So I had this as the q norm of f tilde, and this, after a series of transitions, becomes the p minus 1th power of the p norm of f. If you work out the mathematics, it just turns out to be perfectly fine. Now you just integrate on both sides, raise both sides to the power 1 by q, and this is the exact identity that you end up with. Now what next I can do is, once I have that, then I say that clearly, now I make another statement which I just missed, and I said that clearly f tilde belongs to LQ. Why does it belongs to LQ? Well, I see that the qth power of f tilde is equals to the pth power of f. So what does it mean for a function f to be in LP? It just means that it is pth integrable, that if you take the pth power of it and you integrate it, it gives a finite quantity. But if the pth power of f is equals to the qth power of f tilde, then f tilde must belong to LQ, because again, this is how we define these functions and this space of functions. So I can, since norm of fp equals to norm of f tilde q, I'm so sorry again, if the pth power of f is equals to the qth power of f tilde, then if f belongs to LP, then f tilde must belongs to LQ. And we have the norms as being same, because I just integrated on both sides and I substituted it, and it exactly came out to be this. And finally I say that the norm of psi of f tilde, so now I replace this just by the definition of it. So psi of f of g is equals to the integral of f of g. So I have this thing here, I replace it by this thing here, and then I just substitute the definitions of f tilde. So exactly in the same order I substituted it, and then I brought this f bar to the other side, and then it became f bar. So a bar is norm of, or mod of a square. Then I can write that mod of f square, mod of f to the power p minus 2 is mod of f to the power p, and an integration. So this is nothing but the pth power of the p norm of f, which is equals to this quantity here. And now I got this equation. So the reason why I did all these transitions was for this equation. Now as soon as I have this equation, I can see that the norm of psi of f is equals to the norm of f, because in this section before we saw that norm of psi of f has to be less than equals to norm of f, and thus the equality holds, and thus psi is an isometry. So in the second part of the proof, we are asked to prove that LP is reflexive. So the way I prove it is I start like this. So I say that isometries map complete spaces to complete spaces. So psi of Lp omega is complete since I know that Lp omega was complete. So isometries map complete spaces to complete spaces because the Cauchy sequences in one space converge. So the Cauchy sequences in the other space must also converge because psi is an isometry. But I know that, well, now this is the case for P belonging to open 1 close 2, because for P greater than equal to 2 I have already proved that my space Lp is reflexive. So what I'm trying to do here is, well, my mapping psi goes from Lp to Lq star, and I know that Lq star is a reflexive space for q greater than equal to 2. Well, as of now my point is that psi of Lp omega is a closed subspace of Lq omega star. Why is it closed? Because the psi of Lp omega, the thing over here, is complete and it is a subspace of Lq omega star, which itself is a Banach space, because I know that anything with a star is a Banach space. So complete subspaces of Banach spaces are closed. That's a theorem that we did before. So psi of Lp omega is closed. And now for q greater than equal to 2. So now if P belongs to this, then q must be greater than equal to 2. And I know that for this Lq omega and hence Lq omega star is reflexive, because I did in the theorem above that if you are reflexive, then your dual space is reflexive. So Lq star is reflexive, and I did another theorem before which showed that the closed subspaces, which is psi of Lp omega in our case, that closed subspaces of reflexive spaces are themselves reflexive. So I can say that psi of Lp omega is reflexive, and psi of Lp omega is isometrically isomorphic to Lp, so I can say that Lp is reflexive. Because remember that psi, all I wanted to show that this linear isometry, that this psi, which is an isometry, is also surjective. But of course, surjectivity means that the range is equals to all of space. But if I have this space, you know, this thing as my space, this thing here, if this is the whole of the space, then I can say that indeed my mapping psi is surjective. So I can say that Lp is reflexive. So in the final part, we proved that this mapping psi from Lp to Lq star is surjective. In the case before, I proved that psi from Lp to psi of Lp was surjective. Now I need to prove that this is surjective. Now I know that psi of Lp is a closed subspace of Lq star. I'm skipping the omega every time just to keep the notation concise. Now I know that if the annihilator, so this is the annihilator, is 0, if annihilator is 0, then if you remember, we had a theorem before that if you have a space like this and you have a closed subspace like this is y, this is x, and this is, say, x complement y. If you have an x here, then we used to say that there exists a t belonging to x star such that t is an annihilator of y and t of x is not equals to 0. So if you want to prove that something is a dense subspace, so if I want to prove essentially that this is a dense subspace of Lq, so in order to do that, I need to prove that the annihilator of this is 0, because if the annihilator is 0, if this is 0, then the only possibility that it is that the only possibility that remains is that I can prove that this is dense in the space. So if the annihilator is 0, then psi of Lp is dense in Lq star. Now I take a h, so this is functional in the annihilator of this, so it is the space. So basically h is an element of Lq star star, and the property is that h of psi f equals to 0, because psi f is an element here, because f is an element in LP, so psi f is an element here, and h annihilates it, means that h belongs to LQ star star, and h of psi f equals to 0 for all f belonging to LP. That's the important thing. Now since LQ is reflexive, there exists a G such that this relationship holds, and this is the linear isometry G, and I know that this relationship holds in the case of reflexive spaces. And now I have this equation here, so h is replaced with I of G, and then I of, so if you remember the equation of reflexivity from before, it was something like I of x of t is equals to t of x. So that is here, and then thus I can say that the psi f, so now it's essentially saying that fg is equals to 0. But what was this fg? Well, this fg was psi fg. This operation here is written as the integral of fg over omega. Now this is for all f belonging to LP omega. Now I introduce another g function here. I constructed it like this, so that norm of f to the power p is equals to norm of g to the power q, and f belongs to LP. Now if we just make the substitution here, we'll find out that g turns out to be 0, and since I of g was equals to h, so h turns out to be 0, and that's exactly what I wanted. I took an arbitrary element in the annihilator of psi of LP omega and find out that this h is equals to 0, so the annihilator set must be 0, and thus I can say that psi of LP is dense in LQ, and I know that psi of LP is closed, which I proved in the above case. So psi of LP is equals to the all of LQ, and hence I can say that this mapping here is surjective.